Hello, students, and welcome to the 47th lecture on particle physics. And remember that in the 46th lecture, we had started talking about the GIM mechanism and what was the outcome of that mechanism we have discussed, and how in the experiments the particle was seen. But today we are going to see that why don't we observe flavor changing neutral currents. Just to recall in 5 minutes what we discussed on the last turn, recall that we introduced a doublet for the nucleon. That was the proton neutron doublet, the strong doublet we called, because that was introduced in the case of a strong interaction, that proton and neutron, they are indistinguishable if we switch off the electromagnetic interaction. Then I said that if they are represented by an isotopic spin doublet, then we introduce the isotopic spin operators tau 1, tau 2 and tau 3, like Pauli spin matrices sigma 1, sigma 2 and sigma 3, and using them we introduce the raising operator and the lowering operator that we call by the name tau plus and tau minus. Now using this tau plus and tau minus, we saw that we have n bar tau plus n as p bar n and n bar tau minus n is n bar p. Now applying this to the quark sector, where the member is u and d quark as the doublet, then we have q bar tau plus q, that we are writing it as u bar d, and q bar tau minus q, that we are writing as d bar u. See, still we are talking about the strong interaction doublets, because proton and neutrons are the members of a strong interaction, and here u, d and d quark also they participate in a strong interaction. Besides that, proton, neutron or u and d quark, they participate in electromagnetic and weak interaction processes that we will discuss later. Then what I was telling you that if we have a neutron decay or we have a proton decay, then it involves the emission of a W boson, and the vortex is represented by a GUD, which is nothing but GW cosine theta C. And whether you are talking about proton to neutron, here also the vortex GUD will be represented by GW cosine theta C. And then we discussed that if we have a leptonic vortex, that means a charged lepton is changing to neutral lepton by emitting a W minus, or a neutral lepton is changing to charged lepton by emitting a W plus, or anti-lepton we talk about, this will be W plus, and here a new L bar coming, it is emitting a W minus and it is getting converted into L bar plus, E plus. Therefore this L can, if this is E, this has to be nu E. If this is mu, this has to be nu mu. If it is E plus, this has to be nu E bar. If it is nu mu bar, then this should be mu plus bar, or simply mu plus we call. Therefore the important point is, here we have the vortex, the leptonic vortex, which will contain, the vortex will have GW only. Remember, here the vortex will have GW only. But in the quark sector, if you have U to D transition, then it will be GW cosine theta C or GW sine theta C. Therefore, to start with, in the 60s we had 4 leptons and 3 quarks, and then we realized that there is a transition between U to S and S to U. That was explained on the basis of Cabby-Bow theory, and then we were able to understand that why lambda decay is suppressed in comparison to the neutron decay, And then we also observed that if we have neutron decay with the factor of cosine theta c, then it is easy to understand the neutron decaying into proton, electron, and antineutrino, and muon decaying into electron, antineutrino, and nu mu. Remember, at here when you have all the leptons, then what is actually happening? A muon is decaying, is giving rise to a nu mu by emitting or getting converted into nu mu by emitting a W minus, and this W minus is giving us E minus nu E bar. Therefore, the vortex here, as we know that whether we are talking about neutrino or electron or muon, they are all point particles. Their vertices are the point vertices, and the interaction strength in both the cases will be represented by GW. While if neutron is getting converted into proton, electron, and antineutrino, then this vortex where U to D transition is taking place is represented by GW cosine theta C. And if U to S transition is taking place, then that will be represented by GW sine theta C. This concept should be clear that if we have such type of interaction where only leptons are involved, then the vortex interaction strength will be GW at both the sides. But here, if quark is involved, then this will be GW cosine theta C. And if U to D transition is taking place, if U to S transition or vice versa is taking place, then it will be GW sine theta C. Now, the important point is that is why when we have sine theta C at the vortex, at the square level, matrix element is square level, it is sine square theta C, and that will be sine square 13.1 degree. And if we consider that sine square 13.1, then we can understand why lambda and kaon decay, they are suppressed in comparison to the neutron decay and pion decay. This is what we had discussed till now, and let us start today's lecture from this point. Now see, the transition between the doublet members correspond to SU2 raising and lowering operators. Now this G is representing the strength, and this tau plus will be talking about the transition from D to U. Remember, if we have Q bar tau plus Q. Now in the weak sector, instead of we have UD, we have UD prime. And this we have to keep in mind that when we are writing the current with a raising operator, where we are talking about a transition from a U quark to D quark, then it will be a lowering operator. And when we are talking about a transition from D quark to U quark, we have to use a raising operator, and that is why we have G Q bar tau plus Q. You see here, instead of the doublet U bar D bar, we have the doublet U bar D bar prime, 0 1 0 0 for tau plus, and this is U D prime. And remember, this D prime was D cos theta C plus S sin theta C. Here, therefore, the conjugate will be D bar cos theta C. This should be S bar sin theta C. Okay, therefore, this is U bar D bar cos theta C plus S bar sin theta C. 0 1 0 0, this is U D cos theta C plus S sin theta C. Now you see just the algebra, this will be U bar D bar cos theta C plus S bar sin theta C, and this is 2 cross 2 cross 2 cross 1 matrix. Therefore, this will give us, the product will give us a 2 cross 1 matrix, and that matrix will be D cos theta C plus S sin theta C, D cos theta C plus S sin theta C, multiply 1 with this, and here this will be 0. And therefore, now you see, this is 1 cross 2 matrix, and this is 2 cross 1 matrix. Therefore, we are going to get a number, and this will be, that means U bar D cosine theta C, this will be U bar D cosine theta C plus U bar S sin theta C. This term will be 0. Therefore, what you are realizing that if I take u bar common, then this will be d cos theta c plus s sin theta c. And d cos theta c plus s sin theta c is nothing but d prime. Therefore, notice that if I am taking u bar to the left, we have in the bracket d cos theta c plus s sin theta c, and that is nothing but g u bar t d prime. And g, we are talking about the interaction strength at the vortex. What is that will be clear very soon, because d prime, as you can remember, this is d bar cosine theta c. That means if it transition from d to u bar, then the vortex should contain cos theta c, and when it is s to u, that vortex should contain sin theta c. Now similarly, if we talk about j minus, which is g q bar tau minus q, now following the same analogy, this will be g d bar prime u. And remember this d bar, why we are saying that? Because this u we can take to the right hand side, and this is d bar cosine theta c, remember, plus s bar sin theta c. Therefore, very similar to the above case, where we can write it as g d bar prime u. Therefore, j minus is g d bar prime u, and j plus is g u bar d prime. This is what we are calling it as weak doublets as u d prime. Now, the important point is, we have discussed in the last lecture that tau 3 is not independent. It is related to this tau plus and tau minus. Therefore, if you are drawing some relation with tau plus and tau minus, that should also involve tau 3. And remember, tau 3 was 1 0 0 minus 1. These are all traceless Hermitian and all that thing that I'm not going to detail, because you know the properties of these polyspin matrices. The same is true here also. Therefore, what we have, if there exists an appropriate symmetry based on some underlying gauge theory, then a current involving tau 3 is also expected, as tau plus, tau minus and tau 3 are related via this relationship, remember. And then that means, therefore, with such a gauge theory, one would expect the existence of neutral current of the form. So you see, tau 3 we are talking about. Then we have q bar q. And what is this q bar? Again, this is u bar d bar cosine theta c plus s bar sin theta c. And this tau 3 is 1 0 0 minus 1. And this is u d cosine theta c plus s sin theta c. Again, you see, this is 2 cross 2 cross 2 cross 1. This will be a 2 cross 1 matrix. And 2 cross 1 means this will be u, and this will be minus d cosine theta c minus s sin theta c. Now this is 1 cross 2 cross 2 cross 1. That means this will be 1 cross 1, again a number, and that will be u bar u minus d bar d cosine square theta c minus d bar s cosine theta c sin theta c, that we have this. Then this term s bar d with a minus sign cosine square theta c, s bar d this is s bar, let me just write down it, this is u bar u, then plus sign, we have d bar cosine theta c plus s bar sin theta c times minus sign I can take out, and then we can write minus d cosine theta c minus d sin theta c. Therefore, what you are noticing is d bar d cosine squared theta c. This is s, yes, this is s sin theta c. S bar s, let me make it clear. S bar S sine squared theta c, then the cross term d bar S cos theta sine theta c, and S bar d sine theta c cosine theta c. Therefore, we have what we have? We have neutral current. Why neutral current? Because we are talking about u in the initial state and u in the final state. This can only be possible when you have a Z0 exchange. D in the initial state and D in the final state. This is possible through neutral current interaction. But D to S bar and D bar to S, this is the catch. Charge is not changing, but flavor is changing. Mind it here. If we are writing a neutral current in this fashion, then we are getting a term where we have no change in flavor, u bar u in the initial state and u bar u in the final state, d in the initial state and d in the final state. And but at the same time, we are getting two terms where flavor is changing, but that demands, since charge is not changing, that demands that should be through a Z0. But what I have told you, that flavor changing neutral current has not been observed. Therefore, up to this point, nothing is new. Whatever concept we had from the Cabibbo theory, we stick to this. We had a doublet, weak doublet, ud prime, and we had a singlet, weak isosinglet, that was S prime. But the terms, as you can notice, S bar D and D bar S corresponds to the straightness changing neutral current or flavor changing neutral current, which do not appear to exist in nature. For example, we have K bar mu plus nu mu in the final state. This branching ratio is 64%, while similarly, if one will think about KL0 decaying into mu plus mu minus, this is less than 10 to the power minus 9. That means it is extremely small process. And there comes the GIM mechanism. The GIM mechanism, named after its inventor Glashow, Ilopoulos and Meani, as I have pointed out, is a theoretical concept in particle physics, and that addresses the issue of flavor changing neutral current. Now, what we know, that the weak interaction is mediated by W exchange as well as Z exchange. However, the theory predicts the existence of flavor changing neutral current processes, because we are saying that nobody can stop D to S conversion or S to D conversion up to now, and that is why it is difficult to understand why there is no transition, why we have neutral chaos not decaying into mu plus mu minus, or the various other processes which we have discussed in the last lecture. Therefore, without changing its electrical charge, that is the main, such processes are highly suppressed. We see that it is less than 10 to the power minus 9, extremely small, very, very rare decays or processes. Such processes are highly suppressed by the small masses of the quarks involved, but are not completely forbidden, because all the exact and approximate conservation laws that we have to take into account. If we are following exact conservation laws, then that process should be observed. But what is happening here, that we are following all the exact conservation laws, but still there is something, because of that, the KL0 decaying into mu plus mu minus, that is getting suppressed. Remember the other concept that I gave to you in the second last lecture, delta S delta Q rule. I told you that if delta S delta Q is not with the same sign, the change in strangeness is not with the same sign as the change of charge. If remember, I told you that if delta S is minus delta Q is plus 1, or delta S is minus delta Q is minus 1, such processes are forbidden processes. And this we discussed in the class, that why this is happening. Now here we are talking about a process which is again highly suppressed, not very difficult to observe. The question is why we are unable to observe such processes, and this is explained through GIM mechanism, which was given in 1970. What, according to GIM mechanism, the presence of multiple generation of quarks, up, down, strange, and so on, introduces cancellations among loop diagrams involving W and Z boson exchanges, effectively suppressing flavor changing neutral processes. One of the significant predictions of the GIM mechanism is the existence of charm quark, which was later experimentally discovered. The GIM mechanism provided theoretical support for the existence of this new quark. And what it tells you like we have an isotopic spin doublet UD prime. Similarly, we have another weak doublet CS prime. Therefore, a charm quark was introduced, and this S prime is minus D cosine theta C plus S cosine theta C. Remember, this is Q prime is C S prime, C minus D cosine theta C plus S cosine theta C. So therefore, remember that the thing which we discussed just here, J0 is Q bar tau 3Q. Now we have two sets, two doublets that we are going to discuss. One will be the same as what we have here, and another will come with charm set. Okay, therefore we will have C bar here, and here we will have minus D bar and plus S bar, because that was minus D bar minus D sine theta C plus S cosine theta C. Therefore this will be minus D bar sine theta C plus S bar cosine theta C, and here it will be C instead of U, and this will be minus D sine theta C plus S cosine theta C. Therefore what they did, they introduced a new doublet, and that doublet was CS prime, and therefore this J0 they extended to 2G Q bar tau 3Q plus Q bar prime tau 3Q prime. And this was the interesting result, that we had already Q bar tau 3Q, then we have additional Q bar prime tau 3Q prime. And this Q bar was, remember, U bar D bar cosine theta C plus S bar sine theta C. This was 1 0 0 minus 1. Then this was U D cosine theta C plus S sine theta C. Now in addition to that, what we are talking about, plus C bar minus D bar minus D sine theta C plus S cosine theta C. Therefore the doublet is CS prime, and that CS prime is C minus D sine theta C plus S cosine theta C. Therefore this is minus D bar sine theta C plus S bar cosine theta C, 1 0 0 minus 1, and here we have C minus D sine theta C plus S cosine theta C. This is what we should get when we are considering another doublet, where the doublet member are C and S prime, okay, instead of U and D prime. Okay, now you see this term we have evaluated here. This term we have evaluated here. Similarly, we will evaluate the other term. And what is the important point, that what you will realize, that in the other case, or rather if we look at it carefully, let me erase this part. what you will realize, that we will have a term like C bar C, and with an opposite sign at that we will have a cross term with a positive sign. Therefore, here we have negative sign. There we will get plus sign S bar D plus D bar S sine theta C cosine theta C. And here we will have minus D bar D sine square theta C, and this will be minus S bar S cosine square theta C. Therefore, the extra term that we will have will be C bar C minus D bar D sine square theta C minus S bar S cosine square theta C, then a plus sign S bar D plus D bar S sine theta C cosine theta C. Now when you will add them up, then this will give you U bar U plus C bar C minus D bar D, because sine square theta C plus cos square theta C will be 1, minus S bar S, and then these two terms will get cancelled out. That is the beauty, that when you are considering another doublet, weak doublet with C and S prime, then you are getting an additional term which is the interference term has an opposite sign, and therefore what you are noticing, that we have U bar U plus C bar C minus D bar D minus S bar S. Therefore remember, this is C bar C plus U bar U minus D bar D minus S bar S, and everything else has vanished. And you can notice that we are talking about a charm quark in the initial state and charm quark in the final state, U quark in the initial state, U quark in the final state, and this is possible through Z0 exchange, but this is not carrying any Kabibom factor of theta C, neither cos theta C nor sin theta C, because there is no change of flavor. They are of the same flavors, U bar U, C bar C, D bar D, and S bar S. There is nothing like S bar D or D bar S. There is nothing like U bar C or C bar U. Therefore, the important point is, when you consider this case, then you are getting a term that is 2G U bar U plus C bar C minus D bar D minus S bar S. And thus the unwanted term cancels and only flavor diagonal term survives, U bar U, C bar C, D bar D and S bar S. This is how he proposed a new doublet, that is C S prime, and we were able to understand why flavor changing neutral currents have not been observed in nature. Now in the next class, I will start discussing about the experimental discovery of the charm quark, and we will see that how the efforts of Ting et al. At Brookhaven Laboratory and Richter et al. At SLAC, one was this collider experiment, another was the center of mass experiment. The Ting et al. Did the experiment, the laboratory frame, where the target was at rest and the projectile was coming with certain energy and momenta, while Richter et al. At SLAC did electron-positron collider experiment, and both of them found peak around 3.1 GeV, and that could only be understood if we say that that meson is made up of a CC bar quark. Let us stop here, and in the next class we will discuss the discovery of charm quark. Thank you very much.